Okay, welcome to this short little video on mainly, I suppose, electron diffraction, but in the process we're going to revise what Rutherford found out in his alpha scattering experiment, and then we're going to link this to, or maybe say why it's not very good, and come up with another method, and that method that you need to know about is something called electron diffraction. Okay, so first up, let's just remind ourselves of what Rutherford's scattering experiment actually showed. If you remember, he fired alpha particles at very thin gold foil. The gold foil was a few atoms thick, tens, maybe 100 or so atoms thick, and the expectation was to prove the plum pudding as being correct. All the alpha particles were going to go straight the way through. This isn't what happened. Most went through, some were deflected slightly, and very few were deflected backwards, known as backscattering, and this is what totally amazed Rutherford and his students, Geiger and Marsden. They just didn't expect this, and this is what forced them to come up with a new model for the nucleus, which is what you've probably been studying at school for years, which is known as the planetary model, with a nucleus in the centre and the electrons going around the outside. So, in revision, what did the results prove? Most pass through the foil, so therefore the atom is mainly open space. The volume of the nucleus is much smaller than the volume of the atom, and most of the mass of the atom is contained within the nucleus, and the nucleus is positively charged. So this is what we can deduce from the evidence that Rutherford's experiment showed us. Okay, so we're going to use this. You're going to use the results of the experiment to consider using a similar experiment. I think we're going to look at aluminium in this example, but we're going to look at if the alpha particle effectively has a head-on collision or a head-on rebound from the nucleus. So therefore, it's going to go up to the nucleus, stop, and then return. Now we know at this point the initial kinetic energy of the alpha particle is going to be equal to the electrical potential energy of the alpha particle at that point in the electric field. And what we mean by that point is the distance of closest approach. So using some formulas that we've met before on the A-level course, we're going to say the kinetic energy of the alpha particle is equal to, this formula is the electric potential formula, multiplied by the other charge on the alpha particle. So this is the electric potential energy of the alpha particle at this point. Okay, so what do we know? Well, we know that the charge on the alpha particle is plus 2e. We know the charge on the nucleus, let's just pretend instead of using gold we've used aluminium. So that at that point we've got 13 protons in aluminium, because the Z number for aluminium is 13. So we know all that. So we know Q, we know 4 pi epsilon naught. We want to work out D. So if we consider the kinetic energy, well, remember for an incoming alpha particle, what we could do is accelerate it through a known potential difference. And if we do that, then we can work out the energy by working out the charge of the alpha particle multiplied by the voltage that it is accelerated through. So for a 5 mega electron volt alpha particle, we know that its kinetic energy converted to joules is going to be 5 times 10 to the 6 times 1.6 times 10 to the minus 19, and that gives us 8 times 10 to the minus 13 joules. So as I say, that is just an alpha particle being accelerated through a particular potential difference to give it in energy, in our case of 5 mega electron volts, which we've converted into joules. So using the formula again, I've just put some number in. The charge on the alpha particle is 2 times charge on an electron, 1.6 times 10 to the minus 19. The charge on the aluminium is 13 times 1.6 times 10 to the minus 19. We've got all the others in, 4 pi epsilon naught. D, so here I've just rearranged this. We want to work out D, so I've brought D up here and divided through by the kinetic energy. Now I can put some more numbers in. So 2 13s are 26. E times E is E squared, 1.6 times 10 to the minus 19 squared. 4 pi, our constant permittivity of free space, 8.85 times 10 to the minus 12. And the kinetic energy, which we worked out up here, is 8 times 10 to the minus 13. And if you put all that in your calculator, you should get a distance of closest approach, which is 7.5 times 10 to the minus 15 meters. So at this point, this isn't bad. This is what we're saying at that point, is that the distance between the center of the alpha particle and the center of the nucleus is that. So this is an idea, this is a close approximation of the size of the nucleus, isn't it, if you think about that, because this is from the center of the nucleus to the center of the alpha particle, and this is it's certainly more than the radius of the nucleus. Maybe you could argue, if they do get very close, if the nucleus is bigger than the alpha particle, it's less than the diameter, but it's in the region of. So we've got like an answer that's in the region of 7.5 times 10 to the minus 15 meters. Now, there are some problems with this. Here are the two main problems, and I have just hinted at them. The scattering is caused by individual protons that are located throughout the nucleus. Now, with the formula we've just used, we've just assumed a central point charge. So we've just assumed that our distance r, or our distance d that we've calculated, is the distance between the two centres of the nucleus and the alpha particle, which isn't possibly particularly accurate. So that's problem number one. And problem number two is that we've assumed that the parent nucleus, or the aluminium nucleus, stays where it is, doesn't move as the alpha particle comes in, and what we should realise that won't happen, that there will be some recoil as it comes in. It will be repelled by the incoming alpha particle, and this isn't going to be insignificant because the alpha particle's size is significant. It's got two protons. It's got two protons compared to, in our case, 13 protons. So there is going to be a recoil, which of course is going to affect this distance. So this isn't as good as we'd like it to be, but it does give us a starting answer. So, as I say, don't worry, there's a far better method, and this is called electron diffraction. Now, electron diffraction goes back to some work we did in year 12, and this uses the wave nature of electrons, and we're going to just bring back the de Broglie equation, and we're going to consider the de Broglie wavelength of an actual electron. Okay, and when they pass through gaps, and the gap in our case is that we're going to try and make the electron pass through the nucleus, so the nucleus itself is going to be the gap, and if the gap is similar in size to the wavelength of the electron, the de Broglie wavelength, then we should have diffraction occurring. But first, we've got to do some maths, and we've got to look at what is the wavelength of an electron. And again, don't be worried about this. This is year 12 work. This is the wave-particle duality, and in this case, it's the wave nature of particles. Okay, so here we go. Here's our de Broglie reminder. If you remember the de Broglie equations, it was the wavelength is h over momentum, h over mv. So if we imagine a high energy electron, we need to consider, can we work out what possibly could be the velocity of the electron. Now, the velocity is quite difficult to work out, but we might be able to do some maths so that we haven't actually got to go and measure the velocity of an individual electron. We might just be able to try and get its momentum. Okay, so how about if we accelerated a high energy electron through a potential difference of 1,000 megavolts? So here we go, here's some maths. What we're going to say is the kinetic energy of the electron is going to be E times V, the charge on the electron multiplied by the accelerating voltage, and that's going to be equal to half mv squared. Okay, so let's just mess around with half mv squared. I've moved the m over the 2, so it's m over 2 v squared, and I've just replaced v squared with p squared over m squared. Okay, so p being the momentum, m being the mass. So now m over 2 multiplied by p squared over m squared. All I'm now going to do is cancel one of these m's, because that m will cancel with one of the m squareds. So I'm going to end up with p squared over 2m. Okay, so with p squared over 2m, we're saying that EV, the charge on the electron multiplied by the accelerating voltage, is going to be equal to p squared over 2m. So quick rearrange, let's just say p is root 2 mev. So move the 2m up next to the ev, so p squared will equal to 2 mev, then square root both sides to give you p equals root 2 mev. Now what we can do, we can shove this in our de Broglie equation, the de Broglie wavelength equation. So we know that lambda equals h over p, or momentum, so now we can say that lambda is h over root 2 mev. Alright, so we've derived something here that we've lost the velocity. Remember, this v isn't the velocity, it's the accelerating voltage. So we now suddenly haven't got to worry about measuring the velocity of the electron. Okay, so now we can shove some numbers in this. So lambda equals h over root 2 mev. So h, Planck's constant, over the square root of 2 times the mass of an electron times 1.6 times 10 to the minus 19, the charge on an electron, multiplied by the accelerating voltage, and here we said it was 1000 megavolts, so I've got 1000 times 10 to the 6. So this all comes out at a value of about 3.9 times 10 to the minus 14. So our de Broglie wavelength of an electron is about 3.9 times 10 to the minus 14. Now that is in the region of the expected size of the nucleus. So if we fire these electrons at a nucleus, then we should see diffraction occurring. And if we do see a diffraction occurring, we can maybe do some calculations from the pattern that we get. So this is the pattern, this is the practical that you may have seen in the lab, and you would have seen that there's the electron diffraction tube, and it gives you a pattern like this on the end of the tube. And this is basically what's happening. You've got the electrons being accelerated through a potential difference. They pass through the material. In this case, it's just called a crystal lattice, but this would be the particular material. And then you get a pattern which consists of maximums and minimums. Okay, so you can see there's a maximum in the center, then it's dropping to a minimum, and then it goes to another maximum, and then it drops again. And if you plotted this, you'd be able to plot this with an angle, so the angle that it's scattered through against the intensity that you get on a screen. Okay, so I'll just show you a slightly different picture here. Here we can see that the particle beam comes through, it's diffracted through a particular angle, and it gives you this pattern. So this pattern here would appear on this screen. Now, as I've got some extra notes on here, and an analysis of these patterns can be used to determine the size of the objects the beam is aimed at. Because if you remember from your work in year 12, when you pass light through slits, either single slits or double slits, you get diffraction patterns, and you can use the width of the maximum and minima to work out the original gap size, and that's exactly what's happening here. So the intensity of the diffracted beam is plotted against the scattering angle of the beam, and the angle of the first minima is measured and used in another formula which you don't need to know, but I'll just mention it. The angle of the first minima is used along with the wavelength of the electrons, which is the de Broglie wavelength, and you can use that to get a size of the gap. Now this is the formula, but first of all, more importantly, this is the you need to know. So this will be the intensity, the detector readings intensity, and you see we've got a maximum, and it drops to the first minimum, and then it goes to another maximum, then it drops again, and it'll keep going. So the maximum being at the center, and then the angle where it drops to its first minimum would be this angle theta, and R is the gap that it's passed through, which is the size of the nucleus, and this formula, which is 0.61 multiplied by the de Broglie wavelength of the electron divided by sine of the first minimum, at the angle of the first minimum. And I have seen that mentioned on the odd exam question, but you don't need to know it for the exam. It will be given to you if you needed to use it. Okay, so this angle is used to calculate the radius of the nucleus R, and this gives you much better results. And what you do need to know for the exam is why it gives you better results, and that's what I'm just going to finish off with. And this is the advantage of the diffraction method over Rutherford's closest approach method. So here we go. Electrons aren't subject to the strong nuclear force, so patterns are easy to interpret. If you remember, alpha scattering involved protons and neutrons. This doesn't, it's just electrons are involved, so there's no strong nuclear force to get in the way. Electrons provide much better resolution as they get closer to the nucleus, and the more reading you do on this, it's very difficult to actually understand what's going on because these electrons are passing through the nucleus. The gap is the nucleus itself. It's nothing to do with the gap between the atoms or the gap between the nucleuses. The gap we're talking about is the nucleus itself. So we've got a very good resolution here because they are actually passing through the gap. A practical reason why it's better: high energy electrons are easy to produce in the lab, and as we know, they've got a large charge to mass ratio, so they're much easier to accelerate. They're highly charged with a small mass, so it's easier to get them moving effectively. And finally, in Rutherford scattering, remember, only the closest distance of approach is measured, not actually R. Here we are measuring the size of the nucleus, whereas in Rutherford scattering we are assuming the closest distance of approach is near to the size of the nucleus. So here we're not doing that, we're doing far better, we're measuring the actual size of nucleus.